Our group worked on convolutional neural networks in a hardware accelerator design, and this work was part of the Emerging Devices and Circuits Lab, funded by the Semiconductor Research Corporation. Our PhD mentor was Xiaochen Peng, and our faculty advisor was Dr. Shimeng. And the whole idea behind this project was to kind of replicate what's going on in the field currently, where hardware is mimicking software in order to propel the entire technology industry further.
Machine learning is rapidly growing and it's the future of technology. So it's really important to keep up with its rapid growth. The current hardware has endless capability and reflects the growth of machine learning, which we can physically explain through figure 1. Looking at part A, we have a matrix of node of node and arrays. The node represents the resistors, and the array represents the crossbars. In figure 1 still, part B is the physical representation or the physical implementation of part A. Part B is where we see the electrical components that goes into developing this synaptic crossbar with the resistor and the current modeled below. And our team attempted to develop this design through the following timeline. In August, we did our initial meeting. Going towards early September, we review all the documents necessary for this research design. And in mid-September, we analyzed the machine learning algorithm that are important to conduct and achieve our goals. In early October, we happened to draw a pseudocode that is going to outline how our code is going to maneuver to reach our goal. And starting November, we happened to write a code in Python and then execute that utilizing TensorFlow to gain the weight and the subarrays of our design. And towards the end of December, we trained all members of the group to learn to fabricate the PCB board. Early in January, we determined the type of microcontroller that we are going to utilize to connect the PCB board to the microcontroller and to the computer in order to achieve our goal. Early February, we trained the code to gain the interface. And earlier March, very unfortunately, we happened to draw the schematic, and very unfortunately, we were not able to move forward because our next step today was to print the PCB board and also train our microcontroller and combine them in order to have a working device as we intended.
Our first goal was to demonstrate that a neural network can be implemented physically, as is usually implemented in software. This was done by looking at the different layers of our neural network and picking one layer and a certain subsection of that layer. That way, we could show that a physical neural network can work on a smaller scale and then it can be expanded on. Our second goal was to show that software emulation can be done on hardware, because with our project, we were demonstrating that if you were to implement a neural network physically, then you could still have the same accuracy and efficiency of identifying objects in different datasets, such as the CFAR10 and the MNIST dataset. And finally, we wanted to create a pipeline for future work because our project only composed of finding a single layer or even a single subsection off a single layer of the neural network. But we wanted to potentially show that if this is possible, then you can, in the future, be able to implement a full neural network in hardware and have greater performance results with the same accuracy as a software implemented neural network. The methods and procedures we used were divided into hardware and software categories. For our hardware, we designed a 32 by 32 subarray using the Eagle program, so using its schematic and layout parts of its program. And then due to the coronavirus pandemic, we weren't able to solder, but if we were able to, we would have soldered in muxes and surface mount resistors that would have added to the functionality of the hardware. Meanwhile, on the software end of things, our main method there first was to pre-train the CFAR10 dataset. This was important because we wanted to ensure that our neural network in software had the best possible accuracy. And then what else we did, we recorded the subarray node weights. And recording the subarray node weights was really important because those node weights were being used to design the subarray in Eagle, and therefore without our software results, we wouldn't have been able to know what to do in the hardware.
These were results from both the hardware and software perspectives. Now, these results reflect as far as we got before the COVID-19 outbreak, and later we'll go on to future work that we've laid the groundwork for. Here, what you see is a schematic view of a PCB that we were going to eventually print, and it's a 32 by 32 crossbar array for the pre-trained network that we created based on the CFAR10 dataset. So the 32 by 32 kind of references how here we have 32 rows of resistors, and here we have also 32 columns of resistors. And this is sort of the physical reflection of a subarray from our pre-trained network, where each resistor represents a node in the matrix of the entire array of our pre-trained network. So each of these resistor values here will get filled in based on the results of our network training. Here on the sides, we have multiplexers on either side to select for each individual resistor node so that we can access it and control it from the microcontroller. Down here, we have ADCs, analog to digital converters, that will convert the current read from each column here into a digital value that will get eventually transmitted to the microcontroller and then back to the algorithm.
For the software portion of our project, we developed a deep convolutional neural network in TensorFlow to simulate the hardware integration, specifically the weight quantization that needs to occur to translate the weight data from digital to analog current. The top image shows a code section of the network, while the bottom image shows the results from training the network. What isn't shown is the results from running inference, in which we recorded the weight data of one subarray in the third layer of the neural network, which was used to design the PCB. Our future work consists of printing the PCB, creating the microcontroller interface that will serve as the interconnect between the model and the PCB, testing hardware integration and interface, and getting results by running inference against the pure software baseline to see the differences in energy consumption and execution time. Finally, we would like to acknowledge the previous work of our mentor and advisor, which has formed the foundation of our project.